Hi there. Today we'll look at how to represent part-whole hierarchies in a neural network by the legend himself, Geoffrey Hinton. He describes a system, also known as GLOM, that is a new approach to processing visual information using neural networks. And interestingly, the paper starts off by saying, this paper does not describe a working system. So this is an idea paper, Geoffrey Hinton's suggestion of how we should go about solving vision or furthering vision in the AI community. He says openly, these are just ideas. Please prove me right, prove me wrong, try them out, and so on. And I absolutely welcome this. Idea papers is a thing that I think we have lost as a community because everything needs to be state of the art and so on. This is super cool, and I encourage more people to do it. I'm not saying you're going to have the same kind of success with an idea paper as Geoff Hinton. He is banking on his name in large part with this, but nevertheless, it's just an archive paper. Like, I see people complaining, this would never be possible if it wasn't. Yeah, it wouldn't. Like, people wouldn't pay attention, but you're welcome to write your ideas and post them on archive. Or write a blog post, make a YouTube video. Anyone has opinions. So, go ahead. So to the paper itself, GLOM, as you can see here, GLOM stems from agglomeration, is a system that instead it presents a single idea about representation, which allows advances made by several different groups to be combined into an imaginary system called GLOM. The advances include transformers, neural field, contrastive representation learning, distillation, and capsules. GLOM answers the question, how can a neural network with fixed architecture parse an image into a part-whole hierarchy which has different structure for each image? The idea is simply to use islands of identical vectors to represent the nodes in the parse tree. If GLOM can be made to work, it should significantly improve the interpretability of the representations produced by transformer-like systems when applied to vision or language. That's the abstract. We'll dive into the system. We'll see what it's about. I think I can actually make a suggestion to improve it, but maybe I'm way behind other folks. So, what is the GLOM system and what are these parse tree about and why does it combine all of these things? And for that, we look at, so Hinton has two core diagrams here. This is the first diagram. This is the second diagram. And at first sight, they have little to do with each other. So let me try to go about it like this. If you have an image, and Hinton looks at vision very much in terms of you have an image or a video and you want to parse the image into kind of a tree. And the tree should be sort of like a tree of objects and their parts. So let's say it's an image of a car. So the whole notion is very, very object-centric. So this is like my best attempt at a car. And a parse tree for this image would look something like this. All right, so this whole thing here is a car. So that's going to be your top node in the parse tree. The car has different parts. Namely, it has this cabin, it has a motor, and it has wheels. So that is going to be, those are going to be kind of downstream of that parse tree. Then the cabin itself is going to have two segments here, windows, and maybe here is the door area. So that is going to be window, window, door, and so on. So you get that what we want to do is we want to look at an image and sort of create this parse tree over here. This is very much into the area of GoFi, good old-fashioned AI, people that want to understand the world in terms of their symbolic representations and relation of these symbols to each other. However, what Hinton is saying is that if you simply do this, you can't really do this with neural networks. Neural networks are continuous and so on. So what would you have to do? In addition, we know that the brain doesn't reconfigure itself every single time you get a new input. So the brain, even though it has some neuroplasticity, while you look at the world and do inference in the world, the connections stay the same. So what we need to do is we need to come up with a system that when we input one image, it can give us one parse tree, but when we input another image, it can give us some kind of other parse tree. Maybe now there are two objects in the image, and this one has one descendant only, which in turn has two descendants, and so on. You see the point. The tree structure needs to be different each time. This in part was addressed by Hinton's Capsule Networks. So in the Capsule Networks, Hinton's idea was sort of, okay, I'm going to have these capsules here in different layers, and I'm going to have kind of lots of capsules in these layers, lots of capsules in these layers, and I'm going over capsules because it's kind of important here. So Hinton's idea with capsules was that the first layer of capsules would sort of recognize the smallest parts. So this would be kind of the wheel capsule, and this would be sort of the window capsule, and so on. So there would be a single capsule for every part that could possibly be in an image, right? You already see the limitations. Because if you want to recognize the whole world, you need many capsules. But nevertheless, this was the idea. So a capsule would be active if there was the given object in the image. And then the next thing here, this would be kind of the motor capsule. So the motor capsule, and this would be the cabin capsule, and so on. So the window would activate the cabin capsule, but the door capsule would also activate the cabin capsule, and so on. And the wheel would maybe activate, I don't know, the wheel should probably be here as well. Wheel at this level would activate that, and then all of these things here would activate the car capsule. Sorry. So you can see that this parse tree here is generated dynamically, right? These connections, this routing in capsules is generated every time different. So in the next image, there could be a different object, different capsules are activated, different things are routed together. The parse tree is different. However, you need these many, many capsules for that. Every one capsule per possible part in the image. And that was just infeasible. And also the routing was very cumbersome in these capsules. So here we go with a new approach. And this new approach is what Hinton describes as the GLOM architecture is composed of a large number of columns which all use exactly the same weight. Each column is a stack of spatially local autoencoders that learn multiple levels of representation for what is happening in a small image patch. Okay, so we're going to build up some kind of imagination here. At the bottom level, we have our image. So our image is going to be lying flat on the ground. Maybe you can see it like this. And it is going to be divided into pixels or small patches, whatever you want. But these would be called locations. So it would be divided like this into different locations. I am not good at perspective drawing. In any case, above each location, there would be one of these columns. And these columns, I can draw one here, these columns would sort of stack up like this. And these columns would be divided into multiple levels. So there would be a bottom level, which would be this. There would be a middle level, higher level, and so on. Hinton suggests about 5 levels should probably do. And every single level of this column tries to represent the location at the image, right? This location down here, in a different resolution. So the very bottom level might be aware that there is a part of a wheel. Like let's say this is a cat. So here there's probably, yep. Okay, so you can see there is an ear or a part of an ear let's say it's just a part of an ear in this location. So the very bottom thing would probably represent something like the very structure of the fur. So the bottom thing would represent what's going on at, the micro level, really the location level. The next layer would represent what's going on at this location in a kind of a broader sense. So that might recognize that's actually part of an ear, right? So it goes beyond the location. If you think convolutional neural networks, you're in the right ballpark, but we're going to implement this differently. The next layer will recognize, well, this location is part of a cat's head. And then the next location will recognize, well, this thing is part of a cat. So at this location, there's a cat. Now there is a cat at other places, but at this location there is a cat, and so on. So maybe we don't have more at this particular image, but if you consider a different column, like this column right here, and you look at what's going on in that column, you'll see similar. So in the top layer, let's just consider the top layer. In the top layer, it might say, well, there's a cat too, but it's also part of a cat's neck, and then here it's maybe there's a bunch of a chin, and there is also a fine fur structure of the chin. So you get the idea. Every column will build up these representations, and these are vectors. So these are embedding vectors. So at the bottom location, you'd have the fur vector, and then this vector is the ear, whereas over here, the chin would be very different. It would be a different vector at the same layer. So the only thing that agrees here is the cat vector. The cat vector in this top layer would agree between both of these columns. I hope you get the idea. You have a column above each of the locations. Every single layer in the column represents that particular location, but at a different level of abstraction and a different level of, I don't want to say resolution, but it would consider more and more of its neighbors. The question is, how does it consider its neighbors? And how do you learn these things, right? So how do you learn these different abstractions? And that's where these columns, they communicate with each other. So Hinton imagines that this is a process over time where the columns iteratively communicate to each other, and within the column, the layers communicate to each other. And this is one of these first diagrams right here. So this is one single column over time. Okay, this would be the fur at the ear. This would be the cat's ear, and this would be cat. Okay, so the information so the embeddings are updated by sending information around. Every single embedding, which means that every single vector at every single layer of every single column is updated by simply averaging 4 things. So we have the embedding at layer L at time step t plus 1 is going to be, at layer L location X is going to be a sum between the 4 following parts. It's going to be the embedding at the last time step, right? So this is sort of a recurrent neural network. The new embedding is the old embedding, plus it's going to be a function, a top-down, that's what Hinton calls top-down function, of the embedding at the same location in the previous time step at 1 layer above, so L plus 1. It is also going to be receiving information from the upwards, I think bottom up, calls it bottom up, embedding of layer L minus 1 at the same location at time step t. All right, so that's what you can see right here. The green arrows are each layer simply passes information to the next time step. This is, if nothing else happens, you just keep your embedding. Then each embedding also sends itself through a neural network one layer above itself. That's the blue arrows. So the blue arrows here are these, and everything is a neural network here. Every arrow, except the green ones, but the green ones could be too. So every arrow is a neural network. So this is a neural network sending information above. And this is intuitive, right? So the ear embedding would sort of send information about itself, like saying like, hey, I'm a cat ear. Sends it above, and it goes through a neural network because it needs to be transformed. The neural network has to learn, well, if it's a cat ear at that level, it might be a cat at the top level. And lastly, every single layer sends information down, and that is the red arrows right here. They're also neural networks. So the cat ear says, well, I'm a cat ear. So downstream of myself, there might be, some fur structure, right? So all of these embeddings, they try to predict each other. They try to predict the neighbors of themselves. And Hinton's idea is that by aggregating over time, they will sort of reach a consensus of what is in these columns. Okay? There are a few things missing right here. The one thing that's missing, and Hinton pointed this out, that all of these different columns that we've drawn, they use the same weights. Okay, so, and he discusses this at the end of the paper. It's not really biologically plausible, but there's an ensemble effect. We won't go into that. But all these, so the blue arrows are always the same for each time step, but not necessarily the same between different layers. So that might be, this F might be different from this F down here. However, the function passing information from layer L to layer L plus 1 is the same in every single column across the image. It's a bit like a convolutional network in terms of weight sharing. So you can imagine it as one-by-one convolutional network in that sense. But except the information does not only go up the layers, it also goes down the layers over time. So as I said, this is an iterative procedure. It goes up, down, and laterally. The second thing is, now that you ask, oh, well, if every single column has the same weights, wouldn't that simply sort of, how can you localize any information? And the answer is that you have a side input, like in a neural field, you have a side input annotating each location, basically a positional encoding, honestly. So in addition to what the image patch looks like, you also get your kind of either your XY coordinates, or you could also get your relative coordinates to some other coordinate frame in there. And so the network knows where it is. And that's going to be important because what Hinton wants to build are these islands. So the imagination of Hinton is that this is going to be somewhere in between, like after time step 10, and you want to run it for 100. And he imagines that what will emerge are these sort of islands. So imagine the image is now a 1D vector down here. Or you can imagine these columns in 2D, whatever fits your brain better. But imagine the image is simply a 1D line right here. He imagines that the bottom vectors, they will just, happily kind of be describing whatever that is at the very bottom level. But then at the next level, once it goes to sort of lower resolution, higher abstraction, there must necessarily be vectors that are the same. If this system works, and look at these two vectors and look at these two vectors, they are the same because they now describe objects that are larger than one location, right? The cat's head is larger than simply one location. Therefore, at the layer that represents the cat's head, you expect, because these are all all the up and down functions in the same layer have the same weight, you expect that the embedding of a cat's head is the same in the different columns. Right? This is, if the system works, this must be the case. And then as you go up, you expect more and more of these, what Hinton calls islands, to emerge, right? So they agree. And the idea between all of this message passing is that over time, all of these things kind of reinforce each other. So we looked at a column before, and we maybe said, okay, so this vector down here, it gets information from the top saying, hey, there's a cat here, so you might be like a cat ear or a cat eye or something like this. And then it gets information from the bottom saying, well, there's fur here, and there's some cartilage showing and so on. And it has already sort of figured out that it might be an ear, and these informations, they reinforce itself now. Like they'd be like, okay, you're saying I'm part of a head, and you're saying there's a bit of fur and cartilage, and I already kind of noticed that I'm a bit like an ear, so I'm probably more an ear. So the idea is that over time you have this consensus algorithm. There's one thing missing, and that is, how do the different columns communicate with each other? So I said there are different parts. There is one missing, and that one missing is going to be, I'm just going to call it whatever, A. And A is going to be an attention mechanism across all the other columns at the same layer. So if we look here, this cell receives information from above, from below, from itself, and also in an attention mechanism way, it's going to receive information from all of the different embeddings at the same layer. You can see that Hinton puts in everything we got in here. Now the attention, he says, is easier, and so these are the 4 parts right here. At each discrete time and in each column separately, the embedding at a level is updated to be the weighted average of 4 contributions. The prediction produced by the bottom-up neural net acting on the embedding at the level below at the previous time. The prediction produced by the top-down neural net acting on the embedding at the level above at the previous time. The embedding vector at the previous time step. These 3 we got. And then the attention weighted average of the embeddings at the same level, right? At the same level in nearby columns at the previous time. So nearby, he later backpedals a bit, I think, on nearby and what nearby exactly means. And he, at some parts, so this is idea. I think this is still up for debate. And this is, I think, where I can help. But what he wants to do is he wants to attention aggregate, and he wants to simplify attention. So instead, what we usually have is we're going to produce queries and keys and values. Queries, keys, and values, and they're all going to be different functions of our input. And then we're going to do query times key transposed softmax of that times value, and that is going to be our attention mechanism. That allows arbitrary information to be routed around and so on. Hinton says, nope, what I want is simply that all the queries, the keys, and the values, they're all just equal to the embeddings themselves. So the attention mechanism would work out to be the softmax of x times x transposed times x. And what that does is, if you yourself are the query and every vector also itself is the key, what do you attend to? You attend to vectors that are very similar to yourself. And you can see that in Hinton's diagram. The one we circled dark blue, what would it attend to? Well, it would probably attend to its left-hand neighbor, the one you can see circled. I'm going to circle it. This one, it would probably attend a lot to. This one, it might not attend so much, and the ones over here, it might not attend at all. What does this give us, especially since the values are also these vectors? This is a consensus algorithm. It is not meant as a way to pass information around. It is not meant like in a transformer as a way to do computation, because we have no trainable weights in this process. It is simply meant as a consensus algorithm. So Hinton imagines that by doing this, by sort of attending to things that are similar to you and then integrating their values, there will be these islands forming. And that's what you see right here. You can imagine if two vectors are already close at the same layer, this mechanism will make them even closer. So this is a sort of a clustering algorithm. And so my question is that these drawings, you look at them, they are very specifically constructed. They're constructed such that a parse tree is emerging. So when you look at this, you have a clear sense. I can probably move all of that crap out of the way. You can see the parse tree, right? Because the black thing is going to be the top node right here. Let's leave away the scene level embedding for now. The black thing is going to be the top node. And then it has two child nodes, this one and this one. And then it has every one of those has two child nodes. But it doesn't have to be in this case. So this dynamically, and every one of them, the black ones are individual. This is dynamically constructing a parse tree, right? The parse tree here is something like this. And then So this is pretty cool, but it is also drawn deliberately such that a core problem does not arise. And the core problem would be something like, well, what if this vector here was actually also pointing like this? Okay, so it is not in the same area of the parse tree, right? If you go down the parse tree, it is actually here. Now, if we do what Hinton says, and if for this vector here, we do this aggregation via attention on the same layer, what we will attend to is this vector over here. Now, this is probably not meant to be, because this vector over here, it can represent the same thing, but you can see it's not in the same path of the parse tree. And he mentions this a little bit throughout, but not necessarily clear. And the drawing makes it seem like there's no problem, but I hope you can see how this is a problem. The attention would pull in information from over here. However, the whole parse tree here and the island on the top layer suggests that these two things should be parsed independently from each other and therefore also processed independently from each other. So here is my suggestion to extend this. And maybe Hinton's already thought of this, but I would suggest that this attention mechanism here is modulated by how close two things are in the parse tree. Okay, so what would that be? So for a given vector, it would be how much do you attend to this vector right here? Well, a lot, because it agrees with you, right? The softmax of the inner product would be high. It agrees with you, and also it is in the same branch of the parse tree. So that's perfect, right? This one right here doesn't agree with you, but is in the same branch, so it could potentially later agree with you through a consensus algorithm. However, this one over here, you probably shouldn't attend to that too much, even though it points in the same direction, because it's in a different branch of the parse tree. You shouldn't attend 0 to it, because these branches on top, they could change. And by you sending information there, this one could change the top structure here. That could agree more with your branch of the parse tree and so on. So my suggestion would be that let's not only get the softmax of the current layer things, but let's do x times, and here we're going to have a sum. So this is going to be k, and let's say we're at layer L, and this is layer 1, this is layer 2, this is layer 3. I'm going to number them from the top, actually from the bottom. Layer M minus 1, and this is layer L. I suck at this. So from the current layer, I want to go up the hierarchy until layer 1, and I'm going to take the softmax of the representation at layer L, at layer K, where I'm at, xk transposed, like this. What we aggregate is still the values on the current layer, but how much we should attend to that should be dependent on the parse tree. And we do that like this, and maybe we have like a kind of a lambda k, L minus k. I hope you get what I mean. So how much you aggregate this sum here is weird. This should go probably... Hi, it's Future Yannick, and I just wanted to write that down again. So, because I've made some mistakes, obviously the sum here should be within the softmax, because you want to kind of aggregate the distributions in log space, and the softmax should still be a valid, distribution. And then the lambda is exponentiated by k, and k now properly runs from the 0 to all the way up the stacks. So big L would be the total number of layers, and little l would be the layer where you're currently at. And you can clearly see that the contribution of these attention matrices, it is, so lambda would be something smaller than 1, and therefore the contribution is in the current layer is the strongest, but also in the next one up is a bit weaker, then one more up is even a bit weaker, and so on. So you'd still have essentially the same mechanism as Hinton is suggesting, controlling for the fact that things are in different branches of the parse tree. All right, back to classic Yannick, who is thoroughly confused by these things. Yeah, I'm not good at coming up with math on the spot, but I hope you can see what it's doing. So it is, if you simply take the first k, you would simply stay at that layer, and it would be what Hinton said. But what I'm saying is you should also consider how much your higher layer, one layer up from you, agrees with one layer up from the thing you want to attend to. So you also compute that inner product between the embeddings, and you add that to the softmax distribution. So initially the softmax distribution would be like you should attend to this thing and this thing and this thing a lot. But then the next up hierarchy would maybe say, well, we agree because these are in the same thing, but this one maybe not so much. And you would add those together, maybe with a lambda factor in here, and then you go one layer up, and it would say, well, okay, everything over here basically agrees, right? And here, no. But everything over here basically doesn't agree, so you would add that maybe with a lambda squared. As you go up the layers, it would be less and less important, but still you'd consider it. All right. If this is gonna work out, cite the channel. Now back to what Hinton says. This is actually the system. This is the system as in a nutshell. You're gonna input the image at the bottom, and Hinton says you could use like a convnet at the very bottom to get it into the columns, but then you're going to every time step pass information up the columns, down the columns, and between the same layer of the different columns. And that's going to, in some point, This is going to stabilize. I don't know if it has cycles. It probably doesn't have cycles. This is L. Probably does not have cycles. So at some point, this comes to an end. And if that comes to an end, it should be that the object level embeddings agree on an object. The part level embeddings agree on what parts there are. The subparts agree, and so on. And they form these islands. These islands give rise to a parse tree. And the parse tree can tell you what object is there, what is it made of, and where are these parts in the image, and so on. So exactly, that is it. And now we're going to look at what Hinton calls some design decisions. How many levels are there? About 5. Okay, we can skip that. How fine-grained are the locations? Hinton says you could be as fine-grained as pixels, or they could correspond to larger image patches. And he says you could do convolutional neural network to get it in there. Does the bottom-up net look at nearby locations? He says, yes, the bottom-up net, so this is not the attention network, that's the bottom-up network. It could look at nearby locations, but Hinton imagines that if you have bottom-up, top-down, and if you have attention drawing in information, and if you maybe limit that attention to a neighborhood, then the attention will do the job, because you can have, instead of looking at neighboring locations in the bottom-up network, you can simply in 2 time steps aggregate that information. So you can do bottom-up here, and then using the attention, the lateral mechanism, you can pass that information around this way. And also, it is not as biasing the network to the immediate neighborhood. So the attention mechanism can sort of look farther, which conflicts with what he's saying on top, that the attention mechanism might only be looking at the neighbors. I think there are different possibilities here. And only looking at neighbors is actually one of the solution to the problem of having, kind of similar vectors at very distant locations at down the levels. But I think it's not as good a solutions to simply look at how close things are in pixel space. Because even though things are close in pixel space, they might be far away in the parse tree space. How does the attention work? We've already looked at this. So the way that one location attends to another location is going to be the softmax of the inner product between the embeddings here. And the values are also going to be just the embeddings at that layer. The visual input, he says convolutional net could be used. Color and texture, he says, he gives this example, like if an object is entirely pale or entirely green or entirely, I don't even know how to pronounce this, the color of a part is straightforward. But what color is the whole object? So this entire notion of capsules, by the way, Hinton imagines this as these embeddings represent kind of properties of the object. So that the cat ear embedding represents not only the fact that it is a cat ear, but also different properties about the cat ear, and even its location in the image is in the embedding. And we know that transformers, they must be doing something like this, because we feed in positional embeddings, for example, at the very bottom, and it can still compute things in terms of positions. So there's an intrinsic connection between kind of capsules and the kind of transformer architecture. He says one of the motivations of GLOM was the idea that the whole object has a compound color, which might be called pale green or mauve. And at the object level, every location belonging to the object has exactly the same compound color. So the object is whatever this all over. When deciding which other locations the object level attend to, preference would be given to locations with a similar compound color. So what he's saying right here is that you could give preference to similar color locations when you decide what you want to attend to, but the color isn't as easy as simply saying what color is there in the location that you are at. But you could be, so if this is green and this here is blue, then the bottom layer would say, yes, I'm green and yes, I'm blue, but they could also be saying, well, I am part of a green-blue object, right? And then the higher layer here, you know, attending or caring about multiple or a bigger region, its color would then be, you know, green-blue, and the consensus could reach on, well, we are a green-blue object, even though the object isn't a pure green or pure blue all throughout. So I think, yeah, I think it's a side suggestion. Maybe he has this as a core motivation between the system, but it's just interesting to see how he thinks of things, and he extends the color here to textures and even shapes. The individual texture elements have their own shapes and poses in spatial relationships, but an object with a textured surface has exactly the same texture everywhere at the object level. GLOM extends this idea to shapes. An object may have parts that are very different from one another, but at the object level it has exactly the same compound shape in all of the location that it occupies. Basically saying that, okay, every pixel that's part of a cat head is a cat head, has the shape of a cat head, even though the individual locations might not recognize that. And that information could be passed around through this consensus mechanism over time. So the cluster discovery versus cluster formation, we've seen that, and he makes a lot of analogies to face recognition, but yeah, the clusters are not. The islands of similar embedding vectors at a level can be viewed as clusters, but these clusters are not discovered in immutable data. They are formed by the interaction between the intra-level process that favors islands of similarity and dynamically changing suggestions coming from the locations embedding at adjacent levels. So the core here is really this consensus algorithm that creates these clusters. And yeah, the clustering algorithm doesn't work by simply looking at embeddings and deciding which ones go together, but the embeddings themselves update themselves in order to form clusters. And yeah, this is replicating embedding vectors. This is a response to a criticism that I guess he got, where someone said, well, why do you represent, if you have these, you know, these columns at the bottom, it makes sense, you have all the different vectors, but then as you go up, you know, you have that kind of the same vector for all locations because it's the same object. Why does it make sense to replicate that everywhere and not just have one? Because, you know, in a database we just have one. And Hinton basically says that in order to reach the consensus, first of all, it's important to have different vectors. They might be slightly different, so they might have some nuance in them, because, you know, they might get pulled into different directions from the kind of bottom-up signal than from the consensus algorithm on the same layer. So I believe that it is important here. I think it's just, this is a criticism he got, and then he decided to put this in here. Learning islands. So what we haven't discussed about this yet is how this is trained. And Hinton says this is trained as a denoising autoencoder. Okay. Let us assume that GLOM is trained to reconstruct at its output the uncorrupted version of an image from which some region have been removed. So he goes into self-supervised learning with this system. This objective should ensure that information about the input is preserved during the forward pass, and if the regions are sufficiently large, it should also ensure that identifying familiar objects will be helpful for filling in the missing regions. To encourage islands of near identity, we need to add a regularizer, and experience shows that a regularizer that simply encourages similarity between the embeddings of nearby locations can cause representations to collapse. All the embedding vectors may become very small, so that they are all very similar, and the reconstruction will then use very large weights to deal with the very small scale to prevent collapse. And then he says contrastive learning is the answer to this. So how do you regularize the model such that this consensus is formed. He says contrastive learning might be useful, but you can't simply apply it straight out. So it learns to make representations of two different crops of the same image agree, and the representations of two crops from different images disagree, but this is not a sensible thing to do if our aim is to recognize objects. If crop 1 contains objects A and B and crop 2 from the same image contains objects B and C, it does not make sense to demand that the representation of the two crops is the same at the object level. Okay, so he says that contrastive learning is good, but you have to pay very careful attention at which layer you employ it, because if you go down far enough, then contrastive learning, especially this type where you crop the image into different parts and you say, well, since it's the same image, the representations should agree. Hinton would say, well, at the top layer, yes, but at the bottom layer, certainly not, because they display different things, right? So you have to be careful where you apply this contrastive learning. And he gives a bunch of suggestions on how to solve that. He says things like, well, negative examples, for example, might not even be needed. Well, that's a different thing. So the obvious solution is to regularize the bottom-up and top-down neural networks by encouraging each of them to predict the consensus option. This is the weighted geometric mean of the predictions coming from the top-down and bottom-up networks, the attention-weighted average of the embeddings at nearby locations at the previous time step, the previous state of end, there should be an end here, and the previous state of the embedding. Training the inter-level prediction to agree with the consensus will clearly make the islands found during feed-forward inference be more coherent. So he says you could regularize the model to regress to the consensus option. So it's sort of like a self regression. And he asks whether or not that will lead to a collapse, because if you don't have negative examples in contrastive learning, this could lead to simply a collapse. An important question is whether this type of training will necessarily cause collapse if it is not accompanied by training the inter-level predictions to be different for negative examples that use the consensus options for unrelated spatial contexts. So here is that problem, right? If you use the consensus opinion for unrelated spatial context, that might be a problem. He says, using layer or batch norm should reduce the tendency to collapse, but a more important consideration may be the achievability of the goal. He goes into why regularization could help, and he says, if, however, an embedding at one location is free to choose which embeddings at other locations it should resemble, the goal can be achieved almost perfectly by learning to form islands of identical vectors and attending almost entirely to other locations that are in the same island. And I don't know if this is what I suggested. So I guess this is kind of a convoluted paragraph, and I had to also read it multiple times, and I still don't exactly know what he's trying to say right here. But I think what he's saying is that what we want to do is we want to sort of regularize the network to produce this consensus, right? So we have a bottom-up signal, a top-down signal, we have a current value, and we have the signal from the attention mechanism. Now, what we want to do is we want to reach a consensus such that these islands form. However, if you attend to any sort of things here that have nothing to do with you, you might not be able to reach this consensus, right? I think that's the problem. I think he's touching on the problem that I said before. So what he says is, what you should do is you should simply attend to things that are in the same islands already. So if an embedding at one location is free to choose which embedding at other locations it should resemble, The goal can be achieved by learning to form islands of identical vectors and attending almost entirely to other locations that are in the same island. Now, I think here what he's doing, he makes the case for the attention mechanism itself, right? So he says, if we simply draw in information from the same layer here, any old information might come in and we might collapse or we might never reach consensus because any old information might come in. However, if we introduce the attention mechanism into this whole thing and only draw in information from the selected neighbors that already are in the same group, in the same island as me, then this consensus algorithm works. So if the network is now forced kind of to learn to build these islands of similar things in order to make this consensus work, if we regularize this consensus. So I believe he makes the case for the attention mechanism. I don't think he, in this case, considers kind of the next up layer islands. What I would say is you need to consider the island membership all the way up the columns in order to decide which locations, right? It's free to choose which embeddings at other locations it should resemble. I think, yeah, this is the case for the attention mechanism. Okay, I hope you're still half with me. If not, I'm a bit confused too, but I think what he's doing is he says, contrastive learning would be good. You can use it, but you have to be careful at which layer you do it. Another regularizer to form these islands would be regularize the network to conform to the consensus opinion. However, if you simply aggregate information from the same layer, then that wouldn't work because, the different things in the same layer might correspond to completely different parts of the image. Drawing in information from there would not help you. How do you solve this? By introducing the very attention mechanism that he introduced in order to only draw in information from parts of the same layer that actually are related to you. Okay. The next consideration he does is representing coordinate transformations. So how does this represent coordinate transformations? There was a Capsule Net paper where he explicitly represents coordinate transformations in kind of 4-dimension quaternion space. And he says that is probably not needed because you don't want to, here says, you could represent this by 4x4 matrices. However, if you simply allocate 16 numbers in each embedding vector in order to represent the part-whole coordinate transformation, like the transformation that relates the part to the whole, that does not make it easy to represent uncertainty about the aspects of pose and certainty about others. So the problem here is that we know that humans, when they watch something, right here, when they watch a scene, like this is a chair, and there is a person, a very tiny person on the chair, we don't see necessarily the coordinate frame of the world. What we see is we see the coordinate frame of the chair, like maybe this is the center, and we see the person in relation to the chair. Our brain seems to do this intuitively, and Hinton thinks that a system like this should also do it intuitively. So somehow the coordinate transformations involved going from the eye to the reference through the frame of the chair, and then from the chair to the person, they should be somehow encoded in this network. However, he also says that it's probably not necessary to encode them explicitly as, explicit coordinate transformations, because not only does that make it harder probably to learn, but also you can't represent uncertainty. In fact, you can represent uncertainty, that's the next thing right here, much better by having a higher dimensional thing that you're trying to guess, right? If you are trying to guess a distribution with 3 components, and you simply have a three-dimensional vector, you have no way of representing uncertainty. However, if you have a nine-dimensional vector, you can have three opinions about the distribution. So this is an opinion, and then this is an opinion. And then you can sort of aggregate and you can say, well, I'm pretty sure about these two things because all my opinions are pretty close, but this one here, I'm not so sure because my individual things say different things. Things say things. All right, this video is too long. So that's his argument right here. We don't need explicit representing of uncertainty because by simply over-parameterizing, we can already represent uncertainty well. And we also don't need disentangled position information and so on. Sorry. We don't need different position informations because, again, the network can take care of that. And he gives a good example, like why would you have disentangled coordinate frame if you have an image? And in the image, the picture in it is this. How do you know if that is a rhomboid shape or if it is a rectangular piece of paper viewed from the side? I should probably draw it way closer, something like this. I suck at this. You probably get what I mean. Like if it is a different object, it has the object and the coordinate transformation are dependent upon each other. And so it makes sense for the neural network to actually entangle the two because the two things depend on each other. In essence, he's just saying, don't worry about explicitly representing all of the different things. We got it. Like the neural network can do all of these things, like uncertainty or position and pose transformations. So here he compares it to different other architectures, comparison to CNN, comparison to transformers, comparison to capsule modules, and at the end it goes into video. At the very beginning he says the paper is about actually a video system, and you can kind of see that because we go through this algorithm in multiple time steps, right? You have it's like you analyze an image with these columns, which gives you sort of a 3D tensor with the image at the bottom. And you go in the next time step, you have a new 3D tensor, right? You pass this whole information around with the image at the bottom. And Hinton says, well, why does that need to be the same image? That could also be different images. So you could use the system to analyze video. So what he does is he says, at the same time you do this time step to find agreement, you could actually swap out the video frame, you could swap out the video frame and produce a slightly different video frame. And you could actually have a kind of an ensemble regularizing effect. So as the whole columns here, the whole system comes to a consensus over time, you feed in different information at the bottom. And what he says is that, if this is a slow enough video, then the top layers here could still reach an agreement, while the bottom layers would change rapidly, but that could be sort of an ensemble or a regularizing effect that it even has. So he intrinsically connects these two time dimensions because they would be separate, right? You could input a video and then in each frame you could do this consensus finding algorithm. But he says, no, it's actually cool to consider them together to do the consensus finding while you sort of watch the video. It's just not clear that you always need the same amount of consensus finding steps as you have video frames. So maybe you want to take like 5 consensus steps per video frame or the other way around. Not sure. In any case, I think that's a pretty cool idea. And he says things like, if the changes are rapid, there is no time available to iteratively settle on a good set of embedding vectors for interpreting a specific frame. This means that the GLOM architecture cannot correctly interpret complicated shapes if the images are changing rapidly. Try taking an irregularly shaped potato and throwing it up in the air such a way that it rotates at 1 or 2 cycles per second. Even if you smoothly track the potato, you cannot see what shape it is. Now, I don't have a potato, but I can give you an avocado. So if you give me a second. How's that? Could you track the shape? I don't know. Probably Hinton's correct. All right, he talks about, is this biologically plausible? And I don't want to go too much into this. He discusses some restrictions, like, we still use backprop, and is backprop plausible, and so on. I love this sentence. In the long run, however, we are all dead. And then the footnote saying there are alternative facts. But yeah, he discusses whether it's biologically plausible. How could you modify it to make it more plausible? For example, when you want to do contrastive learning, there is evidence that dreams, during sleep, you do contrastive learning, like you produce the negative examples during sleep, and then during the day, you collect the positive examples, and so on. So I think this is a more speculative part of the paper, but it's pretty cool to read it. And lastly, he goes into discussion. He also says that this paper is too long already. I'm gonna just briefly talk about this. And he trashes the neurosymbolic people a bit, like he trashes the people that say no, neural networks can never do whatever. And he says pretty clearly, look, neural networks can represent trees. I've given you a system. Also, BERT can output parse trees. So shut up, I guess. And he comes up with this GLOMBERT name, which, is already coined. If you wanted to do GLOMBERT, that's already taken. Sorry. I also, by the way, coined the name Megalomania right now. Okay, if you wanna use it, it better be a pretty cool machine learning system and be based on GLOM. All right, that was the paper. I think it's a cool system. It has a bunch of parts that are maybe not super friendly to hardware at the time, like this iterative procedure, but honestly, it is not much more than a recurrent neural network with very complicated recurrence functions. The video extension might be a bit tricky, but the rest and the regularization might be a bit tricky. The exact objective, so the denoising autoencoder objective, isn't super detailed in the paper. He simply says, reconstruct a corrupted version of the input. How exactly the input happens, maybe there's a CNN, maybe the CNN feeds information into actually multiple layers. None of that is exactly specified, so there's lots to figure out. I do think the ideas are very cool, and I love idea papers, and therefore I recommend that if you're interested more, give this thing a read, give this video a like, share it out, and I'll see you next time. Bye-bye.